In the previous weeks, we started to VHDL in combinational circuits. As a reminder and compensation, I prepared this video. In this video, I'm going to go through the details of VHDL, VHDL-based design principles, and examples. VHDL is an acronym for a longer acronym, VHSIC-HDL. The HDL part stands for the hardware description language. VHSIC part is a program of the US Department of Defense that ran from 1980 to 1999. It stands for Very High Speed Integrated Circuit. The program has led to the development of many advanced technologies that we use today. One of its main outcomes is the VHDL language. There are two popular HDLs nowadays, VHDL and Verilog. VHDL is popular amongst industry. Verilog is popular amongst academia because of its simpler syntax. We will continue our labs with VHDL instead of Verilog. Each HDL has its characteristic workflow. In VHDL, the workflow is started with the determination of the specifications. In other words, we need requirements to start any project, right? After the specifications are gathered and a design is prototyped, we start to generate the VHDL code. Following the code generation, the workflow is split into two, one for the synthesis and one for the simulation. In this lab, we will focus on simulation part rather than the synthesis part, since we need real hardware for this part. First, let's quickly go through the synthesis part. After the code generation, the compiled code goes through a process called routing. This process is followed by binary code generation, and finally the binary code is uploaded to a physical device. Of course, some of the parts like RTL design is shared between the synthesis and the simulation parts. In this simulation part, we elaborate the design and simulate the elaborated design with another design called test bench. The output of the simulation is generally presented as a timing diagram of the inputs and output signals. Each VHDL code contains three parts. The first part is reserved for library declaration. It consists of reserved words like library and use. Some special libraries such as work and std are declared implicitly, and others such as IEEE should be declared explicitly. The library declarations are followed by an entity declaration. If you imagine a circuit as a black box, the entity part defines the input and output ports of the black box. In other words, an entity describes the interface of the design. The third and final part of a VHDL code is the architecture part. Architecture describes the behavior of a design, connects the input ports of an entity to the output ports through a series of operations. It includes the actual logic of the design. Okay, let's summarize the things that we talked about up to this point. The library declarations part declares the reusable parts of the other programs in our program to enable them. These declarations might be implicit or explicit. The entity part defines the input and output ports of our design. If you think of the design as a black box, we also define the data types and direction of the data flow. In the architecture part, we define the actual behavior of the design. we map the input ports to the output ports with the help of various bitwise operations. The architecture part is generally the longest part of VHDL modules. We will discuss our example in the context of combinational circuits and left sequential circuit simulation for the later. In this example, we are going to simulate a full adder design. To do that, first we need to create a full adder module and a test bench. Both a full adder module and test bench are just files that include an entity and an architecture. While simulating the full adder, we are going to include the full adder design as a component inside the test bench. First, we need a simulator and a compiler to compile our VHDL codes. In the lab, we have a Windows XP machine with Xilinx Vivado installed, but my working environment is a Linux-based Manjaro system. Because of that, I'm going to stick with open source alternatives. I'm going to use an editor called Visual Studio Code, and for the compiler, I'm going to use an open source one whose name is GHDL. GHDL has a very good user guide that you can always consult, and the working principle is very similar to Vivado. Let's look at the full adder module in the GHDL documentation. We will create our own code from scratch, compile and analyze it as we did in the lab. Let's start with opening a new folder here. I'm going to create a new folder with the name lab compensation and click OK. Here, let's create our first VHDL module. Click this button, New File, and from here, I'm going to write the module's name. Let's say full adder. This will be the module's name, and for the file extension, it is VHD. Click Enter and we have this window. Now, in this window, we have the library declarations, entity, and architectures. In GHDL and in Vivado, the default library's name is work, and it is always implicitly defined together with the std library in the libraries part. So we are not going to define any of them since they have implicitly defined already. For the entity part, let's create our entity full adder. Okay, let's first remind ourselves of the full adder. If you think about the full adder as a black box like this, it has three inputs and two outputs. Of course, this is for a 1-bit full adder. The inputs are named A, B, C in, and the outputs are Cout and Sum. We can define this type of port mapping in VHDL, and the answer to doing that is, of course, the entities. So, let's define our entity full adder. We will define ports here. Remember, they are A, B, C in, Cout, and Sum. Our input ports are A, B, and C in. Their type is bit and the output ports are cout and sum. Their data type are also a bit. Now, the second part of a VHDL module is the architecture part. In the architecture part, we generally describe the behavior of the design. The architecture of the full adder is like this. There are two parts in it. The first part is this part, the space between architecture and begin. Generally, we define variables here. The next part is the part after the begin statement. Here we define the actual logic. Let's remind ourselves of the schematic of a full adder. Let me move this up a little bit. We have again three inputs, A, B, and C in. So, in the upper part, we have actually two exclusive OR gates connected to A and B, and the output of this gate, of first gate, is connected to the other one with C in. Now, we also have two AND gates here. Let me draw the first one here. And this is connected to A and B. The second AND gate is connected to the output of the first exclusive OR and C in. Finally, both outputs of two AND gates are connected to an OR gate. This one is called sum and this one is called cout. With this information in mind, let's define a signal. A signal is like an intermediate wire. For example, if you look at this part, this wire, and also this wire, they're all the same. These intermediate wires can be represented with a signal. So, let's define our signal first. Let's give it a well-defined name like XOR 11, since this is the first output of the first exclusive OR, and there is only one of them. The data type is bit. Now we will compute this part. So this is A XOR B, and it is equal to our signal XOR 11. Now for the second line, it will generate our sum. So the sum is equal to XOR 11 XOR sin or sin. Now let's turn ourselves to this AND and this OR. First we calculate the A and B. And we will take the OR of the result of this. Cout is equal to A and B or XOR 11 and Cin. So this concludes our full adder's output. Each VHDL module to be tested needs another design called a test bench. A test bench is just another design to test other designs. Generally, a design under test or DUT is added to the test bench as a component. You can think a component is a reusable state of a design. The place to define a component is the same for the signals, in between the architecture declaration and the begin statement. The port declarations of the component should also be the same as the corresponding entity, as well as the name of the entity. You can think of a component as a black box inside another larger black box with inputs and outputs. For example, imagine our design is a black box inside a larger black box, like here. Here the component to be tested is like the little box inside of this large black box with all its inputs and outputs. Let's define the test bench first. To do this, I'm going to create another file, and its name will be full adder test bench. Again, in our test bench, we only need the default library, so I don't include any libraries at all. For the entity part, since this is a test bench, a test designed to test other circuits or other designs, we define the entity empty. But for the architecture part, we need to define some things. The first thing to define here is the component. Component full adder, and we will copy the contents from here. Now, each port defined here needs other signals that we can control. Therefore, we will define 5 other signals, and each of these signals will have a similar but distinguishing names. For example, this one is ATB, TB for test bench, BTB, C in TB, some TB, and C out TB. Signal ATB is a bit and has an initial value of 0 since these are input bits and they generally start with 0. Similarly, B and Cout TB signals also have 0 as the initial value. However, some TB and Cout TB do not have any initial values since they are all output bits. Okay, Now we need to map or connect each of these signals to the corresponding ports of DUT. ATB will be connected to A, BTB will be connected to B, and Cout TB will be connected to Cout. We generally use port mapping syntax to show this mapping. We call the port mapping as DUT, design under test. The name of the component to be mapped, full header, port map, and we write the names. So A goes to ATB, B goes to BTB, Cin goes to Cin TB, Sum goes to Sum TB, and Cout goes to Cout TB. We have the wirings as shown in here. We can send signals to our defined signals to simulate the full header's behavior. How can we do that? Let's look at only one example first. So if you write like ATB is equal to 1 after 80 nanoseconds and add one more timing here. So 0 after 160 nanoseconds. First, we need to analyze our modules. Let's clear the console. To do that, first make sure you are inside the right directory, which is the same directory holding the source code. I'm going to use the GHDL open source compiler. For analysis, write ghdl-a and name of the VHDL files. First, full header test bench VHD. When I press enter, it compiled. Then an object file is created and also here work library is created. Similarly, I am going to analyze the full header file. When I compile it, the full header dot O file is also generated and the related entity is added to our work library. Now, we need to elaborate the test bench design. To do that, I'm going to write ghdl-e full header test bench, which is compiled a little bit before. Now click enter and now the full header test bench is elaborated and ready to be run. How can I run them? It can be run with the command ghdl-r full header test bench, and to see the output timing diagram, I'm going to create a file called wave with the dash dash wave option, which is a GHW file. You can open GHW files with the GTK wave program. So write GTK wave and name of the GHW file, click enter, and here it is opened. Now, first we need to add our signals to this timing diagram. So I'm going to choose the top level design and behind the full header test bench, double click each of the signals to insert into our timing diagram. Same as with Vivado, we can click this button here, zoom to fit, and fit our signals in the visible window. As you can see here, in the first nanoseconds, 000, and we have 00 in the output. After 160 nanosecond, A is 1, so 100 is equal to 01, since the sum signal is the least significant bit and Cout is the most significant bit. You can also change other values. For example, let's make BTB is equal to 1 after, let's say, 100 nanoseconds, and this can be observed in the result. To do that, first I'm going to recompile the full adder test bench and elaborate once more and run the test bench. Our wave file is updated. In GTK wave, add signals and zoom to fit. This part is the same, the previous part, but after 110 nanoseconds point, you can see that it is now 1 plus 1 plus 0 is equal to 1 0 or 0 1, which is 2, right? Okay, with this we conclude our lab compensation for the VHDL. We summarize the most important parts and this will be suffice for now.